So what my talk is going to be about really involves Stackelberg games, just like the last speaker. So you're going to see this defender-attacker type of model as well. But it's going to be in a, your timing on that was perfect. I mean, it's just right on time. But it's going to be in the context of some of these optimal protection and attack type of ideas for, and I can just go up and down this, will be fine. Okay, so it's going to be in terms of protecting patches of land. And it's going to be protecting patches of land against somebody that wants to hurt a particular species. And at the outset of this, you're going to be thinking, if you haven't already talked with me about this here, why would somebody want to hurt a species? I don't want you to literally think, now if it's fun for you to think of somebody that hates penguins or whatever it is, that's fine. That's really not literally the motivation. The motivation is, what's the worst thing that can happen? Because once you lose species, you're not going to get them back. So that's when I talk about an attacker, I'm really talking about worst case type of behavior. We took a look at snail kites in Florida. Now, I'm an industrial and systems engineer, I'm an operations researcher, or if that doesn't make sense, I'm a math nerd. I don't know much about all of this, so I had to go learn from my friends in wildlife ecology. And it took me a while to realize that a snail kite was not something that you fly, it's actually one of those birds. So this I was more familiar with, being at the University of Florida at the time. The idea is that these are nomadic snail kites that are very much sensitive to droughts. So it doesn't matter what kind of attack you're talking about. Initially, what we talked about was, think of a region that's discretized into a set of pixels, or patches as they're called. And what can happen to those patches? They can be man-made attacks. I don't want you to think of a terrorist. I just want you to think of maybe a shopping mall that is put somewhere. That's an attack, right? Or a drought. Now, nobody's attacking with a drought. They're just bad things that can happen. So we are concerned about what happens if areas run dry, and they can run dry for several different regions, even in local areas like this. And so this was the focus. It was not initially an application-based focus, but since I'm speaking at this particular conference, I wanted to show you sort of a couple pictures of what this might look like. So our modeling philosophy, and I'll get to the problem in just a minute, but our modeling philosophy was to discretize either in a grid or however it makes sense. For instance, islands might make sense in certain cases. But I want to discretize this into a set of patches, and I'm going to represent those as nodes over here. So I have 3 different areas here, and I have a death state over here. So if you're in my field, you immediately see this as a Markov chain, which is precisely what that is. If you're not in my field, just because it's got a title doesn't mean it's complicated. It's not. If I'm at node 1, I've got a 20% chance of going to node 3. I have a 40% chance of staying where I am. A 20% chance of going to node 2, and I'm good. These add to 1. This is great. And a 20% chance of going to the death state. And then when you're at the death state, you stay there, just as no zombie snail kites. So they are. This is the idea that we have. Now, the other thing that we added into this is we said, okay, initially, the idea is if somebody comes and destroys a patch, or they attack a patch, then what have they done to us? That's one thing we had to figure out. And another thing is, there was this idea that the ecology student came to me in the first place and said, we want to be investigating connectivity. And I said, well, what does connectivity mean? And they said, well, we just want to make sure all the patches remain connected to each other. And I pointed out that mathematically this is not a very interesting problem, and I think in terms of the species application, it's also not a very interesting problem. The idea is this notion of functional connectivity, and I think, I'm going to struggle with her name, but I think it was Angela Fuller that had talked about this on the first day, and she did a great job with that. I won't rehash that. But there is a notion of what is connectivity, what is functional connectivity. What we decided to do was, and I'd like your feedback either in questions or afterwards, what we decided to do was to focus on the problem of keeping an individual in this environment alive as long as possible. When you decide to stay at node 2, that's one time unit. So for instance, I can stay here, one time unit, another time unit, another time unit, and then I pass away. What I'd like to do is to stay in that transient part of the Markov chain, if I'm speaking that language to you, the white nodes here. I want to stay there as long as possible before I end up in the death node. So that is a heuristic way, not a heuristic algorithm, but it is a heuristic representation of what we'd like to achieve. Put simply, we want to keep these critters, whatever it is we're looking at, as alive for as long as possible. Now, how do we do that? Well, as I've shown you here, and if you're more into the mathematics, what I'm doing is I have a reducible Markov chain, and I can compute the weighted expected hitting time via the bottom equation. If you're not within this field, that's okay. I don't need you to understand this in order to appreciate what it is that we're doing. But the idea would be that an attack ends up ends up changing the transition probabilities that are incident to that particular node. So an attack at node 1, for instance, is going to end up influencing what goes on around it. So for instance, maybe an attack on node, I'm sorry, this attack was at node 2. If I'm at node 1, I'm less likely to go to node 2 now than I was before, and that attack probability gets redistributed to nodes, the probability of staying here, node 1, node 3, and to the death node itself. Now, it's a much longer study. We have a no redistribution regime, and what that means is that whatever I lost here, you see I went from 20% to 12%, that 8% got redistributed in this graph over here. We can decide not to redistribute it as well and just send the extra 8% straight to the death node. But that would be like a bear that doesn't realize that there's a shopping mall in the way and just keeps on going to the shopping mall. Now, if you've been to a shopping mall before, you've never seen a live bear, so that's not what bears do. So we decided that maybe that wasn't the best model, although that's something that either model works for a situation like that.
So I just want
yes, sure. Mm-hmm.
In terms of the snail kites, what is this 0.2 reducing to 0.12?
So the idea is, in terms of the snail kites, if this patch is attacked, it might be because there's not enough water over there to begin with. So some of the snail kites are still going to end up going that way, but they're much more likely to decide to go somewhere else. Okay. And there's a few other ways of envisioning this. Another way of envisioning this, and I don't know if I've really got enough time, so I'll have to say it pretty quickly, but another way of envisioning this is that snail kite, that there's an 8% chance that the snail kite rethinks its previous decision and then plays again, if you want to think about it that way. Like if you're playing a game and you rolled the dice and it says roll again, that's essentially what has happened. I use that analogy. My co-authors had no clue what I was talking about, so I don't teach with that anymore. The mathematics behind this, we do have to specify data. I don't want you to get lost in the notation over here, and as I was looking this over, I could have simplified it a bit. But this is the mathematics that come out of a redistribution scheme like this. I really don't want you to dwell on it. And the game comes as follows. You all are going to be the good guys. Whenever I teach, the audience is the good guy and I'm the bad guy, because that's very easy to remember. You all are going to protect a certain amount of patches ahead of time, and then I attack. And I attack only patches that you did not, I don't get to attack all of them, but maybe there's 100 patches, you get to protect 5 of them, I get to attack maybe 6 of them that you didn't already protect, something along those lines. Now, the idea is that I am going to try to reduce the species lifespan as much as possible, because I'm the bad guy. You all are going to act first, and you're going to make protection actions that increase the species lifetime as much as possible, but knowing that I go next. It's like you're playing a game of chess. You go first, I go second. It's a max-min game that we end up playing. And it is a nasty one. If you're a math programmer, you see all kinds of problems over here. Enough for me to use an emoticon, and that's saying something. It is a mixed integer program, which is horrible. It's a nonlinear program. And to an optimization audience, I then spend a lot of time talking about how we can accommodate something like that. The reason I wanted to show you this here was to give you a flavor of it if you're in that field, but also to say that we don't approach this from a heuristic standpoint. We do try to solve these problems to optimality. What makes them difficult, though, is the integrality on this, because it is an integer player playing against an integer player. Typically, we rely on duality concepts to get around that, and you can't do that here. So we had to come up with something else that was a bit more. But I don't want to get involved with all of that. So then the idea is what I said before. These are the formulations. I'm going to flip through them here because I'm just trying to give you a sense of what it is that we're doing. But the idea is that you protect, that's you, protecting things. I attack, but I'm not, what this equation says over here is I can't attack anything that you defend. And here are the dynamics that govern the Markov chain that I had before. So you have to play within this particular scheme. What we ended up doing with this was actually implementing this on the Snail Kite data that took place in 20 patches that we used. I think it's 20 patches. 19 patches plus the death state, which is 20 total nodes. And if I can show you what's going on, the text is too small for you to see, but what we did is the optimal solution was to protect these black nodes over here, and the attacked nodes are the gray ones that you can see. So white ones, those were neither protected nor attacked. And the structural properties that we saw, well, we didn't see any structural properties. The thing about combinatorial problems are that they give you counterintuitive results that you can't easily classify. If you could easily classify them, you wouldn't need the combinatorics. So they are very valuable as a decision support aid. I will not say that I should hand this off to any agency who should just in lockstep agree with whatever we do, but it is a decision support tool. And there are other things that come out of that, but in 15 minutes I want to make sure that I give you time for questions if you have them, if I've left enough time for questions. So what we've been doing from an ecological perspective is we've actually done something that we think really is important in terms of snail kite conservation. From a operations research perspective, the modeling we feel is a contribution, and we're really interested as well in the algorithms that we use to solve this. What I am particularly interested in, and the reason that and I was very, very happy to be invited here, what I am particularly interested in is finding out a little bit more what kind of pressing problems that either we can solve using this framework or a cousin of this framework, or what other kind of problems that you see that might be useful over here. I have a brand new PhD student coming from a fantastic university who's just on fire to do something in wildlife conservation. I would love to be able to continue doing research, and you all are the domain experts, so I'm interested in what you have to say too. Thank you.
Questions?
So you said, I mean, lovely talk. You said though that you believe this is a decision support tool. Now I understand that as a crudely put selling strategy to the agency who might use it.
True.
But what do you see as shortcomings? Why wouldn't they adopt it?
Two things. So the question was, if I'm going to say it's a decision support tool, why do I say that? One, because I know I have to if I'm going to sell it. But from a model's perspective, if I wanted to put a buyer beware on it, the first thing is, what is it that we are optimizing to begin with? This notion of functional connectivity over here that we have, and I'm putting this in the language that I've heard, is one idea. It is not the idea. There are other very relevant ideas that may be species dependent, might be context dependent, and if this isn't the right model, then we need to be using the right objective. I am convinced that this makes sense in certain circumstances, but I am not going to go tell somebody this makes sense in every single context. So the objective, I like very much this game of assuming the worst, because you're looking at system vulnerability, so you do need to treat me as a malicious agent even if there's not a malicious agent. I agree with that. But when it comes down to this part over here, here we are. This objective might not be the correct objective in some circumstances, and I would love to see what some of the other problems are. The second thing I would say very quickly is that sometimes an agency will come to you to say, prioritize the sites that we should protect. And that's not how it works. If I've got a bucket and it's got 3 holes over here and some water's coming out of here and 4 holes over here, if you give me 3 items to protect, I'm going to protect those 3. If you give me 4, I'm not going to protect these 3 and 1 more over here. I'm going to protect these 4 over here. So these solutions don't nest within one another because they're combinatorial. So that's why I think that you got to be a little careful with the real world considerations on that. And let me get in the back and I'll get you. So I don't want to say, so I'm going to characterize the papers with which I'm most familiar, and I'm going to be careful to make sure that I don't paint with too broad a brush on this. Most of what I've seen really does look for, can this species get from point A to point B? And we're trying to look at something a bit broader than that. We're trying to make sure that there's a real important reason that they want to be at a certain patch. So we're taking into account some connectivity to high quality patches in particular as one of our aims. I've seen that done some in the literature. I haven't seen it done in the same. I've seen species move according to Markov chains in the literature, but I have not seen the weighted expected hitting time, that is how long you stay here, as an objective function the same way. The other thing that I think that we're doing is this two-player game where you're really trying to make sure that you're protecting against a worst case event, where you're trying to make absolutely sure that you are not looking at what I might do or what you think is going to happen. It makes sense to prepare against probabilistic failures. It also makes sense, though, to make sure that you've got a robust system that is not that doesn't have a vulnerability in that sense. Does that answer your question?
You can talk.
Okay, sure. I'd be happy to learn more from you. Yeah. Do I have time to take one more?
I guess we can take one quick question.
Okay, maybe the next speaker wants to get up while I do that? Yeah.
Do you have plans then to test the effectiveness of something like this? Like, do they plan to implement it? Where do you see the next domains, like invasive species eradication, something like that? Do you have a list of priorities?
This would be a good one. So I like that idea. I'm using my wildlife ecology friends' domain knowledge to try to get us connected in Florida to get people to take a look at these. So I don't know the status of that right now. I'd love to see it implemented. We do have other research that does the exact opposite of that game, which is to minimize the maximum instead of maximizing the minimum for exactly the invasive species, because that's something that's also a big problem in Florida. Yeah. I'm sorry, I'll talk to the rest of you afterwards. Thank you.